now he is in Leipzig, and the title of the talk I will not quote because everyone will see it.
Okay, thank you. So it's a pleasure to be here and to be able to talk here on this occasion. Actually, Bob Wald has already mentioned a lot of things I will also address. And I'm trying to give a bit more of the background, which then culminated in concepts which Bob has presented to you in the last talk. Let me give sort of a historic overview. So we learned that axiomatic or algebraic quantum field theory is also already 52 years old, and something similar can be said for quantum field theory in curved spacetime, because a paper by Takahashi and Umezawa in 75 was one of the first papers applying quantum field theoretical methods to curved spacetime situations. Actually, there are earlier papers. There's an early paper by Schrödinger where he tries to give we would say now, a generally covariant description of quantum mechanics. Perhaps the first paper which was widely recognized was the paper by Parker on particle creation in an expanding universe. However, I think the field really took off a bit later, particularly with Hawking's treatment of the Hawking effect, particle creation by black holes, and then were other contributions related to that by these gentlemen here. Then, at the end of the 70s, one can say that the field, after having gone through this golden era where it was really a fashionable topic, there came a phase of conceptual and mathematical consolidation with the introduction of Hadamard states motivated by looking for a reasonable scheme for renormalization of the stress energy tensor. At around the same time, contact was made to the algebraic formulation of quantum field theory in curved spacetime for reasons that Bob has mentioned. There was also a lot done then on scattering theory on spacetimes with horizons. And then since roughly 10 years or a little bit more, we have a new stage where several new mathematical techniques have been incorporated into the theory, particularly microlocal techniques. Then the idea of local general covariance has come up and has influenced the development quite a lot. Quantum energy inequalities have been investigated quite a lot. Nowadays we are looking at concepts of local thermal equilibrium. The perturbative renormalization program has been carried out with some success, and we have structural results and axiomatics, as you have seen in the talk before. To start with, and for the purpose of the talk, to keep things simple, let us think that we are dealing with a very simple field theory on a curved spacetime, and let our standing assumption be that we are considering a four-dimensional globally hyperbolic spacetime. A spacetime which is globally hyperbolic has a causal structure which is very similar to that of Minkowski spacetime. In particular, there are no causal pathologies like closed time-like curves and such strange scenarios. So everything is fairly well understood as concerns the quantization of free fields on such types of spacetimes. Still, they are quite general. It is generally believed that all physically reasonable spacetimes be globally hyperbolic, or at least that their physically interpretable parts are globally hyperbolic. Then we have the Klein-Gordon operator on such a spacetime, and then one can show that there are uniquely determined advanced and retarded fundamental solutions, or green functions, some people prefer to say, for the Klein-Gordon operator. And then one can assign to these data a star algebra, and this is generated by symbols phi depending on test functions, such that this dependence on f is linear. You have this hermiticity condition. You have the condition that the field satisfies the field equation and that it satisfies the canonical commutation relations in a covariant form. Right. So, to the Hawking effect. Now consider you have such a quantum field, and consider the situation that you have a mass distribution at early times which is fairly widely distributed, so that you have very little curvature, and you can essentially pretend that you have Minkowski spacetime at the beginning, and that maybe you put a vacuum state in the beginning. Then this mass distribution collapses after some time and forms a black hole. That's the idea. And here these blue rays are supposed to indicate the light rays emanating here from such points. For a black hole, a horizon is formed, and light signals starting within the horizon area would propagate towards the singularity. Now, what Hawking found is essentially that if you consider a scattering situation, you have the initial vacuum state here, then so the modes that propagate through this collapsing matter will be scattered far away. I mean, those modes which here come close to the point in time and space where the horizon forms. And an observer far away will asymptotically see a thermal radiation, whereas in the beginning we had the vacuum state. There's a related effect, the following Unruh effect, and that says qualitatively the following. Suppose we have a quantum field in a Minkowski spacetime, and we have prepared with respect to an inertial system the vacuum state, and now we take a particle counter or thermometer and we accelerate it with a constant acceleration, let's say in the x1 direction. Then this is the trajectory of this thermometer. Then this will measure also a thermal distribution. And the temperature is linearly dependent on the acceleration. Well, these two qualitative effects can, again, qualitatively be combined. Imagine you have the black hole sitting here at the singularity, you have a horizon, and you keep an observer sitting here at a constant radial distance, then with respect to the gravitational gradient, it is accelerated because it keeps the position, and it will also register, for that reason, a thermal distribution. There's also a sort of very heuristic explanation in terms of virtual particle pairs, which by the strong gravitational gradient have a probability, non-zero probability, to get on shell, with one particle having, with respect to the local potential, an excess energy, and so the particle escapes, and the other partner having, with respect to the local potential, gravitational potential, an energy defect, so it goes into the black hole. So that would be a sort of particle picture of the Hawking effect, but this is very, very difficult to make rigorous. And therefore, largely working with particles or thinking in terms of particles is a concept in quantum field theory which in this context, in this gravitational field context, does not seem yet to be very fruitful. For that reason, it has been largely abandoned for the time being. So, some interlude. Actually, this situation, the Hawking-Fulling-Unruh effect, makes contact to algebraic quantum field theory. And I remind you of what we heard yesterday in Steve Summers' talk. So suppose we have a Weidmann quantum field theory on Minkowski spacetime. So capital F should be the field operators. We also have more data. We have a unitary representation of the Poincare group. We have a vacuum vector. And then we can look at the right wedge region, actually here copied from Steve's talk. He has explained yesterday what that is. So then one finds, okay, then one can form the operator algebra associated with the quantum field and the right wedge region. So it's generated by the field operators rather than bounded functions, if you want proper von Neumann algebra, where the test functions have support in this right wedge region. Then you can form the Tomita operator. You can go to the Tomita-Takezaki theory, to its polar decomposition. And then the Bisoniano-Wichmann theorem tells us that these Tomita-Takezaki modular objects in this situation carry a geometrical meaning. The J, the modular conjugation, is a P1CT operator. P means the parity transformation with respect to this axis defining the wedge. And the modular group is the boost group leaving the wedge invariant. And then the consequence of that is that the restriction of the vacuum state to the algebra of the wedge is a KMS state, a thermal equilibrium state, for the boost group. And now this geometrical situation where you have a wedge, where you have a boost group leaving the wedge invariant, is not only relevant for Minkowski spacetime, but also, for instance, for Schwarzschild-Kroskal spacetime, where the wedge actually is the outer region of a black hole spacetime, an extended black hole spacetime. This part here would be the part inside of the horizon. And there's also a boost group with respect to a killing time coordinate outside here, corresponding roughly to the observers that keep their distance to the black hole horizon constant. So these generalizations to static black holes have been discovered, so to say, first I think by Sewell in a completely rigorous form. There were extensions in the context of the Hawking effect by Haag, Naunhofer, and Stein, for instance, and Steve Sobersen. We have also done something in this regard. I already mentioned some lessons from the particle creation effects. So the concepts of particle or ground state in curved spacetime are strongly dependent on certain global or asymptotic reference systems, and you can say these are observers in the sense of distinguished states or observables, which you have to somehow select in order to specify particular states. So the interpretation of physical processes in generic curved spacetimes should not be based on the concept of particles or, say, vacuum states, and Bob has explained a lot about that in his talk. But it should be based on relations between local field quantities, in particular local observables. And this is precisely the view which is also taken in algebraic quantum field theory. So of special interest is this quantity, the expectation value of the stress energy tensor in a physical state, since that appears on the right-hand side of the semi-classical Einstein equations. So one of the enterprises in quantum field theory in curved spacetime is not only that we want to investigate quantum fields propagating on a given classical spacetime background, but since one may expect particle creation effects induced by the outer fields, the outer field may be caused by some classically described mass distribution, but there may also now be quantum corrections when these particle effects become significant. So this is an equation of interest, and it could be called a semi-classical approach to quantum gravity, and one hope is that this way one may learn something, at least qualitatively, about effects that one could expect in quantum gravity, which are different from the usual what we know from classical gravity. So it is not so easy to come up with a good definition of the energy momentum tensor expectation value, because there are various ways how to proceed to obtain such a quantity on a curved spacetime. And a considerable progress was made by an approach due to Bob Wald, who essentially he tried to lay down some general rules or axioms, if you like, that this quantity should fulfill. First of all, it should depend covariantly on the spacetime metric. We would now say it should be a covariant quantum field. Bob has explained what that means in his talk, and I will also later come back to this and explain what that means in a modern description. And it should be divergence-free. Then the first result which was obtained in this paper was that the different descriptions for defining the expectation value of the energy momentum tensor depends locally on the spacetime metric and is divergence-free. So this is a sort of uniqueness result, and there is also an existence result. The point splitting and Hadamard singularity subtraction yields a definition for this quantity with the required properties. Yeah, I come back as a reminder to our model quantum field theory that we are considering here. So nothing has changed on this transparency, except that I should mention there is a C-star algebraic version by Dimmock. And Dimmock has also investigated the structure further at the C-star algebraic level, and he has also pointed at a very important property of the resulting local net of algebras, namely the time slice axiom, which one would of course expect because of the hyperbolic nature of the field equation, but this actually was instrumental for the further development of the theory, as I may point out later. Okay, let me briefly and at a very qualitative level explain to you this Hadamard, what a Hadamard state is and how you obtain the energy momentum tensor expectation value satisfying the requirements that I have indicated. So this bit here is notation. I write the symbol for a state often in these brackets. There is a Weidmann GNS representation where you also need to specify a Weidmann domain if, as it is taken here, actually the algebra corresponds to a would-be algebra of unbounded operators. And then often I assume that I have selected a representation and simply use the same symbol for the represented operators. I do this here. I suppose I am in a representation, and I take a state vector psi in the representation and consider the two-point function. And now to say that this two-point function of the state in this representation is of Hadamard form means this. There's a singular part which is here, and the essential quantity which enters here is the squared geodesic distance between the 2 points x and y, space-time points. There are functions here which are constructed out of the metric and the field equation, and then there is a smooth part, and all the dependence on the state sits in this part, because by definition the singular part of the two-point function is the same for all Hadamard states and is essentially given by field equation and space-time metric. Actually, one needs to take care here. This thing is singular, this thing is also singular, so this needs a careful definition as a distribution. It also needs a global definition of a distribution, so you essentially have to say what happens if there is no well-defined squared geodesic distance between the 2 points, which could also happen if the points are maybe far away from each other. This has been investigated and I would say fully settled first in a paper by Kay and Wald in the 90s. Okay, so let me briefly describe what happens if you have the stress energy tensor for a classical field satisfying the Klein-Gordon equation. Then you obtain the stress energy tensor essentially by looking at this point split expression, applying a certain differential operator with respect to the two variables, and then taking the limit of coinciding points. And essentially the idea here is the same, except that you have to get rid of the singularities. Now the singular part for a Hadamard two-point function is always the same, so you just discard it. And what you then do is you essentially form this expression that you would gain from the smooth state-dependent part of the two-point function. This looks very simple here. You have to take care a bit. This W is not really so well defined as it looks. There is some freedom, and there's also some renormalization freedom. So the resulting expression is not divergence-free. So a renormalization ambiguity or anomaly rather pops up and has to be compensated, which can be done, and this compensating term, which you plug in here to guarantee that the resulting quantity is divergence-free, is again state-independent and constructed locally from the space-time metric. And then there is some other renormalization freedom, which may also be of importance. Okay, but let me now follow a different line of thought. So since this inception of Hadamard states essentially motivated by the wish to have a good definition for the expectation value of the energy momentum tensor, Hadamard states and the corresponding Hilbert space representations have been investigated. I already mentioned that Hadamard states allow a systematic definition of the expectation value of the energy momentum tensor. The Hawking effect appears in a natural manner in Hadamard representations. In a certain sense, there's work by Haag, Naunhofer, and Stein, Vredenhagen and Haag, and Kay and Wald. And Hadamard states define, at least locally, also unique Hilbert space representations. Well, and the next important development was that the Hadamard property of the two-point function of a state can be characterized by the wavefront set of the two-point function. This was found by Radzikovsky and was further developed by Brunetti, Vredenhagen, and Köhler. So just to say the following. Suppose again we are in a representation of our quantum field, and we take a state vector in this representation. Then the microlocal spectrum condition says that the wavefront set of this distribution you get here is contained in the forward light cone bundle. So this is what this picture is supposed to suggest. You put a point X here, and you have this dark gray shaded region here is supposed to depict the cotangent space at X, and then you have the forward light cone sitting here. So this is where the wavefront set is supposed to be. Now, to say that this distribution, that the wavefront set is contained in the forward light cone bundle is technically expressed by saying what it means where the wavefront set is not. This is done in the following way. One chooses some cutoff function concentrated near that point here, chi, and then one Fourier transforms the resulting expression in an arbitrary coordinate system and requires that in directions which are complementary to these forward light cone directions, the expression falls off rapidly in the Fourier directions. And it turns out that this is a coordinate invariant statement, and this gives you the restriction of the wavefront set of this distribution. Okay, so the important result that Racichowski found was that the two-point function is Hadamard if and only if the corresponding state vector fulfills the microlocal spectrum condition, as I have indicated previously. The nice thing about the microlocal spectrum condition, however, is that it is more general than the Hadamard condition, since it can be generalized to nonlinear quantum fields by imposing fall-off conditions on expressions of this form, where you have products of field operators and their Fourier transforms, when the Fourier vectors approach infinity. And then the microlocal spectrum condition essentially says that there is also a restriction on the wavefront set, meaning that this falls off rapidly outside of certain conic sets. And the microlocal spectrum condition can be interpreted as a short distance or high energy remnant of the spectrum condition in combination with the equivalence principle. So it is sort of the natural generalization of the usual spectrum condition to manifolds. Another line of thought is the following: quantum energy inequalities. Larry Ford introduced another condition for admissible Hilbert space representations of quantum fields on curved spacetime. He said they should satisfy quantum energy inequalities, and that I give in its more modern version. That means whenever you have some time-like curve and a positive smooth weighting function, and you integrate the expectation value of the energy momentum tensor, or rather the energy density along the curve. This is here supposed to be indicated by taking the 0,0 components, meaning the contraction with the tangent of the curve. Then there should be a lower bound, and this lower bound should be independent of the states and only depend on the curve and the weighting function one is chosen. The interpretation is when averaging over finite time, it is impossible to extract an arbitrary amount of energy from any state. Bob has already mentioned in his previous talk that the classical pointwise weak energy condition, like this one, for all time-like vectors, is violated in quantum field theory, as one can show generically. You can show this from the Weidmann axioms, meaning that if you are sitting at a arbitrarily chosen points, you can choose a sequence of states such that this pointwise energy expectation value approaches minus infinity. And therefore, the quantum energy inequalities do impose a non-trivial constraint on Hilbert space representations to be admissible. So now the question arises, what is the connection between the Hadamard condition, which can be expressed equivalently as a micro-local spectrum condition on the states you would regard as physically reasonable, and for instance this condition? Well, for Hilbert space representations of linear quantum fields, like Klein-Gordon, Dirac, and Maxwell on generic spacetime manifolds, one can show that the microlocal spectrum condition implies quantum energy inequalities, and this is basically work by Chris Fuster. One can also go back under certain circumstances. For linear quantum fields on static spacetimes, it was found that there are more relations. For instance, the microlocal spectrum condition implies, as we heard, the quantum energy inequalities. Then Chris Fuster and we have shown that quantum energy inequalities also imply the existence of thermal equilibrium states, or rather passive states, which are a little bit more general. And then one can also show, and if I remember correctly, this was basically work by Hanno Salman and myself, that existence of thermal equilibrium states implies the microlocal spectrum condition. Okay, so we have sort of an equivalence of these conditions, and this shows that a microlocal spectrum condition and quantum energy inequalities can be viewed as equivalent characterizations of quantum field states which are dynamically stable. And they also coincide with the usual characterizations of the correct Hilbert space representations when the space-time admits time symmetries. One topic in quantum field theory and curved space-time is, as I have mentioned, the semi-classical Einstein equations. And there a question is what types of space-times can arise as possible solution to such semi-classical Einstein equations. For instance, is it possible that such space-times behave causally in a very strange manner? For instance, could there arise space-times having closed time-like curves, wormholes, or other weird causal behavior? What one could show is that microlocal spectrum condition and quantum energy inequalities put very strong a priori limits to this possibility. For instance, there is a nice result by K. Racikovsky and Wald saying that for quantum field theories in Hilbert space representations fulfilling the microlocal spectrum condition and existence of a causal dynamical law, this is essentially the time-slice axioms, space-times with, I should put here, compactly generated Cauchy horizons are excluded as solutions to the equations of semi-classical gravity. Space-times with these Cauchy horizons are examples for classes of space-times where the idea is that in the past these space-times were causally well behaved, and then at some stage these space-times start to develop closed time-like curves, and you can think of these Cauchy horizons as separating the space-time regions which are causally well behaved from those which develop closed time-like curves. And this corresponds to the idea that sometime in the future an advanced civilization could be possible to set a time machine at work. Another is warp drive space-times. I will not say very much on that, but this is another interesting scenario of a situation where you would something have like superluminal travel in a certain technical sense. I will not say much about that, but there's also a constraint on wormholes. Wormholes means you have sort of tunnels in the space-time that are very short and could connect apparently very distant points in space-time. But in order to have that, if you investigate the Einstein tensor of metrics compatible with wormholes, you find that they must be they must have regions, small regions, in which a lot of negative energy density is concentrated. And that is not compatible with the quantum energy inequality bounds. At least if you require that you would like to have a wormhole through which an elephant or a human being or something could travel. When you would like to rule out the possibility that photons or elementary particles travel through wormholes, then this is more complicated, and the solution is not completely clarified as yet, as far as I understand, although there is recent progress on this issue. Okay, another very important strand of ideas that have influenced quantum field theory in curved spacetime quite a lot is local covariant quantum field theory. And the idea is here the following. We not just consider quantum field theory on a single spacetime, but we think, like in the example of the Klein-Gordon field, that actually something like the same type of quantum field theory could be assigned to any globally hyperbolic spacetime. And this is what this assignment here is supposed to indicate. So for every globally hyperbolic spacetime, you assign a quantum field and a corresponding net of local algebras and so on. And now the condition is that if two spacetimes have isometric subregions, then the Hilbert space representations of the corresponding quantum field theories restricted to the subregions have to be isomorphic. So here you have isometric patches, and then the restrictions of the quantum field theories to these patches in this spacetime theory and this spacetime theory should be isomorphic. And it was noticed by John Dimmock already in, I think, his first paper on the algebraic formulation of the free quantum fields in curved spacetime, that this gives a functorial description. However, he has not considered the possibility that this holds, so to say, for local embeddings, but this gives sort of the full strength of the condition. So I have copied here the definition from the paper of Brunetti, Friedenhagen, and myself. So the idea here is that you can embed some spacetime isometrically as a part of a larger spacetime. Here you have the assignments of quantum field theories, of algebras to the spacetimes, and then such an embedding is accompanied by an endomorphism of these theories. And important are these covariance properties. I think we are going to hear more about this by Chris Fuster in his talk. So, and if you have that, then a covariant quantum field is a natural transformation between certain functors. One functor is the functor of test functions on the spacetimes where you assign to each spacetime the class of test functions, and where the relation for isometric embeddings is here functorial given by the push forward. And then similarly here you have a local covariant quantum field theory. And so quantum fields are now natural transformations. And the essence of this is that I have this transformation property. So if you push forward a test function from this manifold to this manifold, and consider this corresponding quantum field operator, then this is the same as taking the field operator with the original test function and applying the morphism. And the stress energy tensor of a linear quantum field defined before is local covariant in this sense. So obviously you can generalize this from scalar test function to spinors, tensor fields, and whatever. there are some important structural results making use of local general covariance. First is spin-in statistics, and the statement is: suppose that the quantum field theory fulfills the Weidmann axioms on Minkowski spacetime, because we have a copy of the field in Minkowski spacetime also. Then the quantum field theory has the correct relation between spin-in statistics on each spacetime, inevitably. Next result is PCT by Stefan Hollands, and this assumes that you have a operator product expansion around each point in spacetime for the quantum field, as was described in Bob Wall's talk. And then the result is, for each given spacetime, there is an antilinear operator relating the operator product expansion of the quantum field on the given spacetime with the operator product expansion of the conjugate charged quantum field on the same spacetime but with a reversed spacetime orientation. Well, and linear quantum field theories, they satisfy all the assumptions you need for these theorems, so they're examples. So perturbative construction of interacting quantum field models. Time is running, so I might not say very much about that. Again, you start from, say, the Klein-Gordon field here as an example, from a free field theory within the general covariant framework. You assume microlocal spectrum condition. Then you can define normal ordered products and time ordered products of the field operators to all orders as operator value distributions. And the first step is infinite renormalization, and this has already been described to us by Klaus Vredenhagen in his talk. Also that there remains a renormalization ambiguity. The important point is that using general covariance, you can reduce this renormalization ambiguity quite a lot, and you can also set up this construction process of normal ordered and time ordered products in such a way that they fulfill the principle of general covariance. And in particular, the remaining ambiguity in the definition of these quantities is up to only finitely many parameters for each order of perturbation theory. Meaning that if you, here you have one definition fixing some renormalization ambiguity somehow. Here you have another description. Then the difference in the ambiguities, so to say, or the ambiguity is a polynomial in the normal ordered products and the curvature quantities. And you can give a formula for that, which is important. So that's the main thing. So recently, Stefan Hollands has extended this construction to gauge theories, in particular to Young-Mills in curved spacetime, which is important because this brings us very close to to the perturbative construction of really physical quantum field theories in curved spacetime with all the desiderata you would like to impose, like microlocal spectrum condition, general covariance, and so forth. Yeah, I'm drawing near to the end of my talk. So there's a long list of things I have not treated. Well, you can do superselection theory on curved spacetime. This was already mentioned in John Roberts' talk. And I won't say anything about that here. One can further look into the von Neumann algebraic structure of Hadamard representations. This has also been done. I haven't said anything here. There is a good deal of work about scattering theory in curved spacetime, and I haven't said anything about that here. There is something to say about spacetimes having conformal boundaries, which in a sense is connected to the notion of holography in quantum field theory. There's work by Rehren, by Da Piaggi, Morenti, and Pinamonti, and I think we will hear more about that this afternoon. Well, geometric modular action on curved spacetimes. Stephen Summers has explained yesterday what geometric modular action means. One can also give examples of geometric modular action in non-flat spacetimes. There's also a lot of investigations about quantum field theory on special types of spacetimes, like de Sitter still has a lot of symmetry, but also some features which are significantly different from Minkowski spacetime. There's a series of work also by Bro, Epstein, and Moskela. New reference dates on Friedmann-Robertson-Walker cosmological spacetimes and new results on cosmological particle creation allow a better and quantitative description of particle creation effects in expanding universes, for instance. And those can now be done essentially by first principles without approximations, and there's ongoing work about this topic. A very interesting thing that I'm also working on are local thermal equilibrium states. These are of very great importance for cosmology. When you look into books of cosmology, then temperatures of elementary particles in the early universe appear everywhere on almost every page, and it's very hard to understand what this really means in a quantum field theoretical context, and there is a lot of work on this, and I think more will come in the future. The next 50 years. I hope I have shown to you that quantum field theory in curved spacetime now reaches a sort of mature state. We have a sort of axiomatics and we have applications, and further development will make it possible to calculate effects relevant to cosmology from first principles, I think. Thus it is likely that the importance of quantum field theory will be growing again, and a lot, of course, as with every physical theory, depends on the appropriate blend of conceptual clarity and applicability. Quantum field theory in curved spacetime once was a very fashionable topic. Some people may regret that it is perhaps not at the moment, and that the methods we use are still a bit remote from the methods that theorists use in cosmology. Cosmology now is a very fashionable topic. So some people may regret that we are not traveling on the mainstream. On the other hand, I think what quantum field theory in curved spacetime can do, especially in combination with methods from algebraic quantum field theory, is something that really only quantum field theory in curved spacetime can do. And in this sense, we are absolutely irreplaceable. And I end with this caption.
For this beautiful survey, comments, questions? I have a question concerning the non-uniqueness of the Hadamard 2.5. Have you applied the classical conditions that should go to zero if the 2 points are in space-like direction?
Well, one could do that. One could impose asymptotic conditions, but they would presumably depend on the space-time structure. So for a given space-time which has a certain asymptotic structure, you could do that. And you could perhaps see that there are preferred Hadamard states with a preferred asymptotic condition.
I would even conjectures that make function unique. Of course, you have to have strong conditions in space-time, that's clear.
The problem is to match the Hadamard condition, which is a local condition, a short distance condition with a large distance.
But I mean, I have not. Yeah, I mean, of course, once you have a specific space-time with certain structure you are referring to, then you can try and search for special Hadamard states, which obey special properties.
Pure states,
for example. Yeah. For example.
Other questions?
This Rudolf-Sommer's transplantation of local nets, is that just an instance of general local covariance, or is it something more?
That is the question. I mean, I'm not sure about that. Maybe Chris will comment about that. Because the construction of the net is different. And one can have sort of a bunch of conditions what it means that a theory is local, or put differently, depending on certain starting points, you can construct local nets in various ways. And then the question is, what is their relation? And the construction of this modular construction is different from other constructions where you start from some local fields. So this, the connection is not clarified at all.
Just a comment that this transplantation frequently leads to nets which have trivial algebras for small integers.